Hey guys, Coach Davis here. Another little tutorial for our teleschool time and just a discussion about exponential growth and decay. Uh, Probably have heard quite a bit about this in the news. It's funny because I know you guys always ask, when am I ever going to use this? And here is one time where you may not use it, but it pays to understand what they talk about. I was looking at the Washington Post, and they have an article about COVID-19 and how it's a very simple math lesson in exponential growth. And then just a few minutes ago, I was looking at a video from Fox News that says right now the cases in Michigan double every 3 days of COVID-19. So that's kind of an interesting thought, and that's what we're going to talk about today. That is the perfect example of exponential growth.
Okay, so what you see here is the normal formula for exponential growth. We'll make one change for something called exponential decay. So growth is obvious, we're going to get bigger, and we usually write this in terms of time, a function evaluated at time. Don't get confused at that. On your calculator, it's still the x, okay? And all things have to start with an initial amount, okay? That's what your a is. It goes outside your parentheses. We have a rate of growth. You're going to get a percentage, like 12%, and then you're going to convert that to a decimal. This should always be less than 1. And then t is your time. That's how long this is going to grow for. Before we go into any examples, I do want to talk a little bit about exponential decay. If something grows, it's got to come down eventually, right? Notice it's the same formula except for a minus sign. This is where our 1 minus r will be less than 1. So this is going to be your practice today. First part of it, I'm going to go over numbers 1 and 2 on my whiteboard, and the directions say label if the equation represents growth or decay, and determine the growth decay factor and the growth decay rate. And it says remember to write your rate as a percentage. Okay? So you see the two equations, they'll be at the top of your page, and 1 plus r and 1 minus r are the decay factors. So as I do number 1, you're going to see me break that 1.35 apart. Okay? Here's number 1. Now first things first, I want to look at this value. If that value is bigger than 1, it is a growth formula. We are growing. So now, I said my rate and my factor. The factor is the 1.35, okay? But if I wanted to, I could write that as this. I'll take either one, okay? Now, it pays to break it up like this because this gives me my rate. Okay, that gives me the R rate. So R is 0.35, but rate needs to be a percentage. And remember, we're going to move our decimal place 2 places to the right, and we get 35%. And that's what number 1 should look like. As we're just breaking them down. Now, if we wanted to go a little step further and say, well, what's this going to be in 2 months? We could change the x to 2 and go from there.
You know, one of my favorite exponential growth subjects is called compound interest. Dave Ramsey talks about it quite a bit in his Financial Peace University when he talks about investing. And when it comes to money, you're always trying to find ways to make your money work for you. And compound interest is the way to do that. My seniors, when we did this, heard me say Compound interest is the eighth wonder of the world. That is a quote attributed to Albert Einstein. Okay, so let's take a look at compound interest. If you have a savings account, you kind of know what this is because every so often your account's going to get money. Not money that you deposited, just extra money that the bank puts in because you have an account with them. And they'll compound it every so often. Let's take a look.
So here we have the formula for compound interest. And it looks kind of weird, but let's go through it just slowly. P. In finances, our initial amount is called the principal. That's what we're depositing in the bank. You start a savings account with $100, the $100 is your principal. Rate. That one should look familiar from the other equation. This is the interest rate that you're going to get. Most of the time for our examples that we're going to do today, 4, 5, 6%, which is really, really good. Time. The amount of time you're going to have your money in the account. Those three should be familiar. The N is a new one for us. N is it says the number of compounds. That's the actual amount of time, or the number of times that your account is going to have money put in it per year. So there's a lot of different ways you'll see it. And you got to think about what are the number of months in a year, for example. Days in a year. One of my favorites is bi-monthly, which is 2 times a month. There are 24 of those. Let's take a look at a few of them. This is the terms for your end value that you're going to have to know. So when you hear the term it compounds annually, that's going to compound 1 time a year. There are 4 quarters to a year. Really means every 3 months. But if you see quarterly, we're talking about 4. Monthly, there are 12 months in a year. Weekly, there are 52 weeks in a year. And daily. For this argument, we're going to use 365. Let's look at example 1. You have the compound interest formula there, and it says you have $3,000 deposited in an account that pays 4% annual interest compounded monthly. How much will be in the account after 20 years? All right. So think about the problem. It told us that our principal, or P, is $3,000. That's what we are depositing in our account. We're getting a rate of 4%. Change the percent to the decimal. Remember, 2 places to the left, so 0.04. Compounded, monthly. Monthly is 12. And then our T, it told us we were going to keep this in the bank for 20 years. All right? So here we go. So the setup looks like this. So we got 3,000. We know we got 1. Our rate, N, how many times are going to compound. And what this is really doing is breaking up the 4% over the 12 months. And then N, which is 12, times 20. This number, your exponent, is going to give you the value of total compounds over the time it's in the account. So in this case, that's going to compound 240 times. There are going to be 240 times that you're going to have money added to your account. Now, at this point, all I've got to do is put it in the calculator. So let's do that. All right, so let's take a look. So we're going to put in our initial value, 3,000, parenthesis, and I'm going to put it in just like I had it on the board. 1 plus 0.04 divided by 12. It's important that you close the parentheses. Now we're going to exponent, And I can just simply go 12 times 20. Calculator will take care of it for me. Enter. And at the end of 20 years, you will now have $6,667.75 in the account. Now, I know my seniors, when we do this, I talk about, well, that's not a whole lot of money, which I'd say, okay, but did you work for any of that money? And the answer to that is no. You're going to get that no matter what you do to that $3,000. Pretty cool, huh? This is one of those. Here's the reason why you need to know exponential growth.
All right, guys. We will all be on today. If you have any questions, please be sure to check OneNote for your assignment. And other than that, stay well and see you soon. Bye.